Welcome everyone to the first in a series of videos where I'm going to be solving some common chemical equilibrium problems. Now, a few things to know about these videos. These are not lesson videos, okay? I'm going to be solving specific types of problems that will hopefully help you as you go through the myriad of equilibrium problems which exist. For each video, I'll try to highlight the most important types of prior knowledge that you're going to need to be able to solve these problems. First thing is that going into this, you really need to know and have a clear idea of what chemical equilibrium is. Second, you should have already been introduced to the equilibrium law, okay? So this shouldn't be your very first exposure to that equation. And finally, and this applies to all equilibrium problems that we're going to be doing in 4U chemistry, and that is you need to be able to solve solution stoichiometry problems. And you need to be able to work with the molarity equation. You need to be able to work with the dilution equation. And if you don't remember those or aren't familiar with those, I go back and watch a few of those videos so that you refamiliarize yourself with those tools that we'll need to solve the equilibrium problems. Here's our problem for today. And in this question here, we are given information about the initial concentrations of a chemical system. And we allow that system to come to equilibrium. And our task in this question is to calculate the equilibrium concentrations, and then based upon that, determine the value of the equilibrium constant, okay? So this is a common type of problem where we know the initial concentrations. We are given one of the final equilibrium concentrations, and that allows us to calculate all of the other concentrations at equilibrium, as well as the value of K. Okay, this isn't just a made-up problem. This is an important scenario. You know your givens going into the system. This isn't just a made-up problem. This is an important type of question because it shows us the value of the equilibrium law. That if we know the quantities going in to the system, and we know the system's reached equilibrium, and all we need to do is calculate one equilibrium concentration. That allows us to calculate a whole bunch of other things. So let's switch over to the whiteboard and solve this problem. To start off with equilibrium problems, we look at the balanced chemical equation. Always check to make sure it's balanced because that will definitely have an impact on the equilibrium law. So here's our equation. Next up, it's always a good idea to write out the equilibrium law to remind yourself of what we're trying to find. Here's the equilibrium expression for this chemical system. Recall that the equilibrium law states that at equilibrium, the concentrations of the products raised to the power of the coefficients in the balanced chemical equation divided by the product of the reactants raised to the power of the coefficients in the balanced chemical equations is equal to a constant. So a few things you have to remember. This law applies to concentrations at equilibrium, and that's what those little e's are beside my concentrations. Recall that this also only applies to concentrations. So we'll see that in this question, we're given mole values, so we need to express those as concentrations. So our next step here is going to be to organize these values, starting in 3, 2. Our next step here is going to be to organize the given information into a way that we can solve this problem, and that is going to be using an ICE table. Here is my ICE table. At the top, I have the balanced chemical equation, and on the left-hand side, I have 3 rows: initial concentration, the change in concentration, and my equilibrium concentrations. Let's start off by putting in the given information from the question. Now, if we look at the given information in the question, we see that the quantities given are moles. However, we are interested in concentrations. So what we need to do here is take the molar amounts given and divide by the volume. Here are my concentrations before calculation. I'm going to calculate these now, and just for the sake of clarity in this table, I'm going to replace these calculations with the concentration values in moles per liter. Now that I've placed my givens in the ICE table and expressed them as concentrations, I'm ready to do some calculations. So let's imagine what's happening in here. A certain quantity of PCl5 and PCl3 are placed in a closed container. That system is not at equilibrium and allows to come at equilibrium. How do we know it's not at equilibrium? Well, we just know from the question that we start off with no chlorine gas, and then at equilibrium, we have some chlorine gas. So clearly, the reaction has shifted to the right. The question is, what's the extent of the change that is occurring? An equilibrium system works stoichiometrically. So for every 1 mole of chlorine gas that's produced, we're going to produce 1 mole of PCl3. And for every 1 mole of the products which are produced, we consume 1 mole of the reactant. So I don't know how much is going to change here. So this is what the variable x is going to be used for. It's expressing the change from the initial to the equilibrium concentrations. The signs on the reactant side and the product side have to be opposite. If you don't know which direction the change is occurring, just choose opposite signs. It turns out it does not matter at all. I get the numerical values here for x, or the coefficients, based upon the ratio in the balanced chemical equation because these reactions occur stoichiometrically. It's a 1 to 1 to 1 ratio. Now I'm going to place in my equilibrium concentrations for my unknowns. Here are my initial concentrations. Note that I didn't write it in for chlorine gas because we were given that information. What we want to do now is solve for X, and we can do that using my chlorine gas information. The equilibrium concentration of chlorine gas is equal to the initial concentration, 0, plus the change, which is X, and that's the value that we know, which is going to be 1.0 times 10 to the negative 3 moles per liter. And so we see that that gives me my value of X. Now that I know my value of X, I can solve for my other equilibrium concentrations. So take a moment now and substitute our known value of X into the other two equations for equilibrium and find out the equilibrium concentration of PCl5 and PCl3. Here are the answers to the first part of the question. The equilibrium concentration of PCl5, 3.35 times 10 to the negative 3 moles per liter, and the equilibrium concentration of PCl3, 0.15 moles per liter. And if we wanted to calculate the quantity of moles, we would just multiply by the volume of the container and just go back that way. You'll note that when I'm writing out these concentration values, I'm using the subscript E there to organize which values I'm talking about. One of the trickiest things about equilibrium calculations is that there are a whole lot of values and there's some things that we cannot combine. And one of those would be initial concentrations and equilibrium concentrations. And sometimes we just have so many concentration values, it's just difficult to keep track. So keeping yourself as organized as possible and not doing too many steps in your head is very valuable here. Final part of the question was asking to solve for K. To solve for K, we need our three equilibrium concentrations, which we have up here at the right, here, and here. So now that I have these values, I can solve for K. Let's go back to our K equation and substitute those values in. Here's my answer for K. The equilibrium constant at this temperature and pressure is 4.48 times 10 to the negative 2, or 0.0448. Even though you could include units for the equilibrium constant, I will avoid those and we'll just treat it as dimensionless. It's just as a constant value. Let's go back now and summarize the steps that we did in solving this problem. Now that we've solved the problem, let's summarize those steps that we went through. First, we checked to see if the equation was balanced, and if it wasn't, we ensured we balanced the equation. Then we created an ice table, but before we plugged the values in, we took those given quantities and converted them into concentrations. Okay, that's not always needed, but we did that. We always check. We took those concentrations and placed them in the ice table. Then we needed to find the change. The change is based upon the mole ratio. So we use that mole ratio to determine the change. That was an unknown. That was our X value. In our example, the mole ratio was 1 to 1 to 1. So all of our change values were X. The only difference was that we remembered to use opposite signs, positive and negative signs, for each side of the chemical system. So if one side is increasing in quantity, the other side is decreasing. Next, we solved for our unknown. We took that value of x and we used that to determine the quantities that we were trying to solve for in the question, which in this case were the equilibrium concentrations. And finally, if we are finding the equilibrium constant, we remember to use the equilibrium concentrations to do that when we're subbing in and solving for K. Note that steps 6 and 7 there, those aren't cookie cutter steps. This takes a little bit of problem solving because every question is going to be slightly different in terms of the information that you have. And I'd almost say steps 5, 6, and 7 because the mole ratio is not always going to be the same. So it takes some practice, but these are the general steps that we're doing when we're solving this type of equilibrium question.